So we're going to talk about a new family today of organic molecules, and that's the alcohols. And so I'm going to go through and just kind of talk about a few you may have heard of or know of from just your experiences in life. So one is methanol. Methanol, as you might be able to guess, has only one carbon because of the word meth in it. But methanol is a alcohol that's used in top fuel cars, racing cars. You'll get methanol in them because the way it burns, it creates a lot of energy for vehicles better than gasoline does or diesel does. And so methanol is used in racing cars, some of them. At least that's some of the cars will use that. Ethanol with two carbons in it because the word ethanol, that's what's in the drinking alcohols, beer, wine, liquors. That's ethanol. And so that's the one you would have some familiarity with too, just living in American culture. That's pretty abundant in places. And so when people are talking about the alcohol in liquids for drinking, that alcohol is specifically ethanol. In fact, it takes quite a bit of ethanol compared to methanol to do some damage. For instance, if you drank one shot, about 30 milliliters of methanol, that would probably kill you because methanol is really, really toxic compared to ethanol. Ethanol would take quite a bit more alcohol, drinking ethanol, quite a bit more than 30 mils to kill you. So the toxicity of those two for us is very, very different. So all these alcohols are not created equal, and that's pretty amazing given the fact that really the only difference between these two is one carbon. Essentially, as we know, meth has one carbon and eth has two carbons. So just that small difference in the molecule makes a big difference to our ability to handle it as human beings. Another one that you have in your medicine cabinet probably is isopropyl alcohol. This is the alcohol that gets rubbed on your arm, let's say at the doctor right before you get a shot. It's on those little pads that you wipe on. You might have a small bottle at home that you use for various things. Again, cleaning wounds is a good thing because alcohols kill bacteria, and that's why they're doing it. So when they rub that on your arm, they're killing the bacteria that lives on your skin, so that when they poke a hole in your skin with the needle, the bacteria doesn't go inside your body. Your skin's a wonderful defense system to bacteria. You can touch things on the surface of a table. It probably has bacteria on it, but it's not going to get into the inside of your body because the skin is going to block it from getting inside. But anytime you put a hole in your skin by a cut or getting a shot, you always want to clean the surface of that because you're trying to kill the bacteria that may have gotten in. Because if that gets in, bacterial infections can get kind of nasty. A lot of people die from bacterial infections, in fact. And so this is something you always want to do. So if you ever get a cut or a scrape, wiping it with a little bit of alcohol is definitely beneficial for you because it'll reduce reduce the chance of a contamination. And so that's what that's good for. So they're very good very good disinfectant. And isopropyl, notice this is not the normal system we would use to name. So before you're learning when you're naming a molecule, the way we're doing it is a standardized way of naming organic molecules that was developed a while back. But before this system was developed, and the system is called, and you may have seen it on a homework or on a quiz, that's the system that we're using, and that's the international system that was developed by scientists just as a systematic way to name molecules. But before that system went into place, molecules were named, but they were just given sort of common names. Or they were just given names, they just called it something. That may be similar to the way we name molecules today, but not exact. So isopropyl alcohol is something that has been known and been used for centuries, and so it was called isopropyl alcohol at the time. What we would call it now, if we were naming it, it would actually be 2-propanol is what it would actually be called. And so that would be the name, that's an OL. That would be the name of the actual systematic way. So that's what you'll learn it to be. But some of the old names just stick around. And so they're still prevalent in our society, even though it doesn't follow the naming that we are learning in class. The last one I'll talk about is ethylene glycol. Again, this is a name that came about and doesn't use the systematic nomenclature that we are learning. But this is basically antifreeze. So this is what goes into your vehicle, into the radiator to keep your engine cool. It's the stuff that's usually green or orange in color, and so that's in there, and that's basically an alcohol. Alcohols have lower melting points, so they don't freeze as easily as water does. You may know some people who put alcohol in the freezer. Where water would freeze, the alcohol just stays cold. It doesn't actually freeze. You need to get a lower temperature than that. And so that's the same thing with your antifreeze that goes into your vehicles. They are alcohols, and so since alcohols don't freeze at 32 degrees Fahrenheit, they freeze at much lower temperatures. Your antifreeze usually doesn't freeze. Now, it may have frozen during our more recent cold snap, but typically they can get down into the negatives and still not freeze, depending on which alcohol it is. So let's name these guys. Alcohols have a OH on them. And so if you're looking at the molecule, it kind of looks like an alkane, but one of the substituents is an OH. You're not dealing with an alkane anymore, you're dealing with an alcohol. And what we do when we name these guys is we basically name it like the alkane, and what we're going to do is when we do that, let's remove the E in ane and add OL. So when you identify it as an alcohol, we're going to remove the E from the name and add in the ane part of the name, in the family name, and we're going to add OL to it. Then what we're going to do is we're going to have find the longest chain. It's going to sound familiar with the OH. And what I'm talking about, longest carbon chain, that includes the carbon that's attached to the OH. So we're not really counting the OH in this longest chain. We're just going to count the carbon that's attached to that OH. So that'll all be included. And we're going to number it so the carbon with the OH gets the lowest number possible. Right? And this is really what we did with the alkenes and alkynes, right? We found that carbon-carbon double bond. So that was we had to make the longest chain that included that carbon-carbon double bond, and we gave the carbon-carbon double bond the lowest number possible. So again, when you identify the family, you want to make sure the thing that's identifying it as the family gets the lowest number possible, and it's part of the longest carbon chain. And then we got to put number of carbon with OH before parent name. And this is, remember, we got to say where is the OH group. Is it on the first carbon, the second carbon, the third carbon? So we got to include that information as well in the name. Okay, so let's go ahead and get some examples and try some of this out. So here's one right here. Go ahead and pause the video, name this molecule, and then come on back and we'll go through it. So the first question I ask myself is, what family is this? And I can see an alcohol, an OH group, and so I know I'm dealing with, in this case, I don't see anything else of interest. I don't see a carbon-carbon double bond, a carbon-carbon triple bond, nothing like that, nothing cycled, so it's not a benzene ring, nothing like that. But I just see a carbon attached to an OH, and so I'm dealing with an alcohol. So therefore, notice it's like an alkane where I'd want to put ANE, but in this case I remove the E and I add an OL. So that's what I do. Now I find my longest continuous carbon chain that contains the carbon attached to the OH. So here's my carbon attached to the OH right there. So that carbon has to be in the longest chain. And I can go ahead and number this, and let's do that. Here's 1, 2, 3, 4, 5, 6, 7. So it's 7. So therefore that's hept. So I have a heptanol. Now I have to identify where is the hydroxyl group. Is it, since there's 7 carbons, which of the 7 carbons is the hydroxyl group on, or the OH group? So there's 2 ways to number this. So I've numbered it in red. Let's go ahead and number it the other way in purple. 1, 2, 3, 4, 5, 6, 7. And so again, because I'm naming this as an alcohol, I have to have the carbon that has the OH on it have the lowest number possible. And so if I did it by the red numbering, it'd be a 5. If I did it by the purple number, it'd be a 3. And so this is going to be 3 is the proper. So the purple numbering, the one I did second, going from the right to left, is the proper numbering. And so this is a 3-heptanol, much like we did with the heptenes, or the alkenes and alkynes, where we put the carbons with the double or triple bond at the lowest number possible. Same here. So now we just go through and identify any substituent. Now OH is not a substituent because that's part of the family, so I don't have to name that one. And notice everything else is just a hydrogen except for this. And we can identify that as a methyl group. And we can see it's on the, again, we're using the purple numbering, not the red. So this is a 5-methyl. And there's no other substituent, so alphabetization is easy with this. It's only one thing to put in there. So it is 5-methyl 3-heptanol. Okay, this one's going to challenge you a little bit, so go ahead and give this one a try. Pause the video, then come on back and I'll go through the naming of it. Okay, so with this one again, we have to identify the family. And I can see the family here. Notice I got a carbon attached to an OH. So notice everything else is just carbons and hydrogens on this molecule. And so this identifies as an alcohol. And so again, since this is an alkane with an OH on it, I would go ahead and go ANE, but I get rid of the E and add an OL. I have a cyclo, carbons in a ring, so it's a cyclo, and I have 5 carbons in that ring. And so we know this is because there's 5 carbons in the ring, we know it's pent, and since they're in a ring, I got to add the word cyclo to it. So we have a cyclopentanol. We have to say where is the OH group, on which carbon is it. Again, since it's a ring structure, I can start anywhere, so I can make the carbon with the OH on it the number 1 carbon. And so this would be a 1-cyclopentanol, and the 1 in this case you wouldn't have to necessarily put on. That would be up to you. If there were if there were multiple things, then you might have to, but in this case you don't have to. But I like to put it in there just so I remember every time I do an alcohol, I have to put a number in there somewhere where that OH group is. But if you ever see it without the number, it's pretty much given that it's on the 1 carbon. Okay, so now I have to name any extra substituent. I see one right here, and I see one right here. So this is a methyl group, and this is an ethyl group. So I have a methyl and an ethyl group. Now, because my number 1 carbon is already set, there's only 2 numbering choices for me. I can go in a clockwise manner, so that'd be 1, 2, 3, 4, and 5, which puts my substituents on 2 and 3. Or I could go the other direction, which we'll do in purple. Again, the 1 is always going to be the hydroxyl group because I put that in the lowest number possible because it's the family. There's 2, 3, 4, and 5 are my choices. So in the purple numbering, it would be 4 and 5. Obviously, 2, 3 is lower than 4, 5. So my proper numbering is the red numbering at 2 and 3. And so with that, it'll be a 2-methyl group and a 3-ethyl group. So now I just put them in alphabetical order. And I get, sorry, I'm going to not be on one straight line here. It'll be 3-ethyl, 2-methyl, 1-cyclopentanol. So now we'll try it the other way. I'll give you the name of a molecule and you're going to go ahead and draw it. So go ahead and pause the video, draw it on out, and then come on back and I'll go through it. So as I say, I usually like to start from the right-hand side of the name and work my way left for the most part. I always start with the parent name though, so it's not really all the way to the left. I like to start with how many carbons are in the longest chain that contains the family. And so in this case, it's oct. So I just like to draw it straight across my page, 8 carbons. And I don't put anything on them, I just write out 8 carbons. 6, 7, and 8. And just to keep myself, make sure I'm putting everybody in the right spot so I don't have to keep recounting, I'll go ahead and number them. It double checks that I wrote the correct number of carbons, and it will also help when I'm putting substituents on. I can find the carbon very easily and not miss it by 1. So there it is. I see then that it is in the alcohol family, so there's got to be an OH on it somewhere. And where is the OH? Well, that's the number right here. It's on the 4 carbon. And it doesn't matter if I put the OH on the top or the bottom. It would be the same either way, and so that's true here. I can put there on the top. So now there's my alcohol, and now I just need to start putting on all my, well, this made no sense. Actually, this a 1-methyl would actually make this a 9-carbon chain, so that doesn't make sense. So if you put it on the first carbon, you did it correctly. It just, I didn't name it then correctly. It should have been a nonanol. So I'm going to put this on 2. So I can put my methyl group on 2. What I was saying there is if you put the methyl group on 1, notice now my longest chain is not 8 carbons, it's 9 carbons, so that doesn't make sense. So I'll just put on the 2 carbon. But if you put on the first carbon, you did the best you could. It was just not named correctly. So I'll just put on the 2 carbon, then it doesn't change, then it's more of a correct structure. On the 5, so that takes care of this group. On the 5 carbon, I need to put an iodo group, which is just an I. So I got rid of that guy. And then on the 6 and 7, I need bromines. So I'll put 1 down there, and I'm going to put 1 up here, because again, it doesn't matter. So I took care of that. So that's everybody. I got them all on there. Now I just need to decorate it with hydrogens. And so, again, if you put the C8, the methyl group on the 1 carbon, that's fine. That's what you were supposed to do, but it really wouldn't be an octanol anymore. Again, you just got to make sure all your carbons have 4 bonds to them. All your hydrogens, bromines, iodines have one bond to them. The hydroxyl group has one bond to the OH. The O has one bond to the carbon and one bond to the hydrogen. And, right, because this is really, I write it as OH, but just understand that it's really O and it's bound to an H. So the oxygen does have two bonds to it and the hydrogen does have one. And then again, I drew the CH3, the methyl group here. I drew the CH3, but understand that CH3 is really a little bit more shorthand notation for that. And that would be the correct structure. Okay, I'm just going to talk about two reactions of alcohols. The first one is a dehydration reaction. You know what hydration means. It means getting water or adding water. Dehydration can be just the opposite. It can be losing water. So let's take just a generic alcohol. So an alcohol will have an OH and an H, right? Well, it'll have an OH, and then it'll have a bunch of other stuff, but one of the carbons is attached to an OH, and some carbon next to it will have a hydrogen on it. And in a dehydration reaction, we can take that molecule and we can remove a molecule of water, which is OH and H. So we're going to remove this guy, and we're going to remove that guy. And when we remove those guys, we get H2O. So there's our loss of water. And what are we left with? Well, it turns out that the carbons get double bonded together. So essentially what happens here is one of these bonds moves up to here, and one of these bonds moves down to here, and we get that. So we start with an alcohol, and we end up with an alkene. In fact, you know this reaction already because we actually learned it when we talked about alkenes, but we went the opposite direction. We went this way. We took an alkene and hydrated it by adding an OH and an H, right? By moving those bonds and forming it like that and getting rid of all this and forming an alcohol. So we've already learned this reaction, we just learned it in the opposite direction. So basically this reaction can go either way. We can hydrate an alcohol or hydrate an alkene to make an alcohol, or dehydrate an alcohol to make an alkene. And your reaction conditions will force it to go one way or the other. So let's do one. Here's an alcohol. Go ahead and determine the products of the dehydration reaction of this alcohol. So go ahead and pause the video and then come on back. Okay, so in a dehydration reaction, we're going to lose a molecule of water. So we got to go find an OH and an H group. So we'll take this OH and we take an H next to it. Don't take this one because the H doesn't come off the same carbon as the OH. Notice if I pull those two off, they're coming off the same carbon. So it has to the H has to come off a carbon next to it, not the same carbon. So this is the hydrogen that'll be removed. And what's going to happen here is we're going to take this bond and we're going to form a new bond between these two, which gets rid of this one. And then this bond will move down here to form a double bond, and therefore we'll get rid of that one. So that's what we'll form, and there's our products. So our products are, and of course, these two together, we can just rewrite as H2O, or if you want to, you can rewrite it HOH, either way. It's the same. And we're also left with this molecule right here, which is an alkene. In fact, that's 1-butene is the molecule there. So we made water plus 1-butene. So So the second reaction that I want to talk about is an oxidation reaction. Oxidation reactions are many times shown by this little O in these brackets on the arrow that of the reaction. And that O just represents some oxidizer, so something that will oxidate the molecule. So in an oxidation reaction, what happens, oxidation of an alcohol, what happens is, in this case, we remove the hydrogen that is attached to the oxygen of the alcohol group. So we remove this hydrogen, and we remove one more hydrogen that is on the same carbon. So the only other, so that shares that same carbon. So this is the carbon of the alcohol group. And so the only other hydrogen attached is this one, so we remove that one as well. And then what we do is we create a double bond between the carbon and the oxygen. So our final product would be that guy right there. And so that's our product of the oxidation reaction. So when we do an oxidation reaction, all the action happens on the carbon that's attached to the alcohol, or the carbon attached to that oxygen. So let's do one more of these. So here's a oxidation reaction of an alcohol. So go ahead and see if you can determine what the product would be. Pause the video, then come on back. Okay, so when we do an oxidation reaction, again, we find the carbon that's attached to the alcohol. So there's the carbon attached to the alcohol. We remove the H of the alcohol group and remove another H that's attached to that same carbon. So it doesn't matter, you have two choices. You have this one or this one. It doesn't matter which one you pick. We're just going to go ahead and get rid of one of them. And then, of course, a double bond is formed between the carbon and the oxygen in the process. So now we can go ahead and rewrite our final product, which would be the first two carbons in the group are not affected, so we just draw them the same. And then the third one will have a double bond to the oxygen, and I have one more hydrogen left over, like that. And so again, every carbon now has 4 bonds to it, even though that last carbon almost doesn't look like it doesn't look right, but if you count up the number of bonds, because there's 2 going to oxygen, 1 going to carbon, and 1 going to hydrogen, it's got 4 bonds, and the other 2 carbons have 4 bonds as well, and so that's our product right there.